Hi, welcome to my video. Today I'm going to be solving part 1 of exam 1 that we were assigned for our Transport 2 class. And in this problem we are given a Stefan tube which has the length of Z from the vapor phase and then a liquid phase at the bottom where it's going to be heated and turned into the vapor with air blowing high over it at a high velocity. So acetone and methanol are currently in the liquid phase at the bottom of the Stefan tube, where we are having that vapor liquid phase represented as 0 along the Z-axis. And so the Z is actually going to be the length of the tube where we only have vapor up until the screen and the air starts filtering over it. But the whole delta from that is actually 0.24 meters as a whole. So using that, and along with a bunch of givens that we won't be using right now, we'll be using that more in part 2, we are going to be tasked with trying to find the overall question is really trying to find what the molar fluxes are for N1, N2, and N3, and then pretty much trying to solve that out based on coding it. And so really to get there and get started with coding it, we need to scale the whole system down to make it more from 0 to 1, make it more applicable and easier to use when coding in a computer, and then use the order of magnitudes then to find the initial guesses that we're going to try to find based off of the scaling that we will do. And so really we're going to be using a initial value problem and trying to find the answers while coding, which is going to be the end goal of this whole thing. And so really to start, we'll look at this and examine and just analyze what we're really dealing with at the current moment. And so when we look at these up here, I went ahead and wrote down the Maxwell-Stefan diffusivity equations for component 1 and component 2 here. And this is just really the rate of change of the mole fractions of component 1 and component 2 with respect to Z, which is the vapor phase as it moves through it. And really, when we're looking at it, we see here that we have specific variables known as N3, which would be the molar flux of air throughout the system. And because air is being blown over at a high rate, it's not diffusing down. So there's no air diffusing actually down into the system here. And we can really take this out of the system and really make it 0 because there's no movement of air down into the tube. And so these N3s will be equal to 0. And by multiplying these together, it pretty much takes away the entire number, because multiplying by 0 gives you 0. Takes you off, and then you're going to be giving a negative on the right side of that coefficient. But that'll be coming down to another time. So to start here, and when we're looking at it, we really need to set a scale. And really to get that scale, we need to find a term known as eta. So eta is known as the distance Z, that would be any point along this vapor phase, divided by delta, which is the overall total length of the vapor phase. And so what this does really is that this scales it down from a scale from 0 to 1. So there's really no other number that can come out of this other than the fact that we are scaling it more on a basis that we can code a lot easier. And so by scaling that, we have given a dimensionless number from 0 to 1 based on whatever distance we want to pick away from the vapor liquid phase. Okay, so now that we have defined eta, we have eta here, and we know what that is equal to, we can rewrite these two equations, the Stefan-Maxwell equations that we have, in terms of eta. And so this comes out to be dy1 over dz is equal to dy1 over d eta multiplied by d eta over dz. And so once we're given this, we can then go ahead and take the derivative of this part right here, and that will give us 1 over delta multiplied by, I believe it's, dy1 over d eta. And so this right here is what we will want to use to go ahead and put into our equations. But to make it a little easier, I'm just going to go ahead and make a whole new variable to account for us putting it into that equation. Because if we were to put it into the equation as is, we would end up having to multiply by a delta to make it even on both sides. but I'll go ahead and take care of that, because by doing this, which we will do is set a new equation, F12, and this will be equal to, excuse me, the concentration multiplied by D12, which is the diffusive constant, what we are given between the two components, and then over the length delta, which will account for that delta that we see here if we were to input this directly into the equation. And so now that we are able to scale it and we have this given to us, we can go ahead and try to find the order of magnitude that we will need to start with our initial guesses for the coding part of the exam. And so with these guesses, we can use that to go ahead and try to solve what the actual fluxes should be in the system for components acetone, methanol, and then there won't be any for air because it doesn't, once again, it does not diffuse down into the system. And so now that we're looking at this, we can rewrite the equation as dy1 over d of eta equal to pretty much y1 n2 minus y2 n1 all over f1 2. And so this here is our new equation that is given to us after we substitute all this in and really even it out. And so once we start looking at this, we need to figure out what the order of magnitudes are for potentially N1 and N2 so that we can take those guesses and put it into the code that we'll try to find out. And so when we're looking at this, we know that dy1 is going to be a factor of 1 and d eta is also going to be a factor of 1 because we found this here. It's going to be on a scale from 0 to 1, and dy1 is also on a scale from 0 to 1 because it's all the components of the mole fractions will come up to 1. So 1 and 1 on the left side, then that leaves us on the right side because the right side will have to be equal to the left side, which is equal to 1. So take out the easy ones. We'll just go ahead and get rid of y1 and y2 are also going to be on factors of 1. Because once again, it's for the exact same reason as dy1. It's going to be on a scale from 0 to 1 already because the summation of the mole fractions will be equal to 1 anyway. So these will be on the factors of 1. So what we're left with is really n2 minus n1 over this f1 2. And so because this is what we're trying to find, we can't really do anything with that at the moment. And so we're gonna have to go and find what F12 is. And so F12, looking back up here, is CD12. We can write out C is equal to the pressure over the gas constant multiplied by the temperature. And so we know here that the pressure is given, all the stuff is given right here. So the pressure is at a factor of 10 because it is 99.4 kilopascals. So actually it's not a factor of 10. It will be a factor of 10 to the 5th. So yeah, so that's actually going to be that. So the gas constant will be, it's actually roughly 8.314. So that will be a factor of 1. And the temperature is going to be, what is it? 325. So that will be about 100. So factor that out. That will be written that into there. And so now that we have this, we have pretty much what we're looking at here. We're going to rewrite the F12. I'll rewrite this down here. So what we have is 10 to the 5th all over 100 multiplied by D12. And so D12 is actually going to be 10 to the negative 5th. That's just something you have to know for a gas when it's given to you. It's always going to be 10 to the negative 5th for millimeters squared per second. You want to change that over to meters, and it will be 10 to the negative 5th. So 10 to the negative 5th here. These cancel out. And on the bottom, we were given with 1. So really, this whole thing is going to be equal to 10 to the 3rd. And so now that we know that F12 here has an order of magnitude of 10 to the 3rd, and this whole thing has to be equal to 1 on the left side, we know that the difference of N2 and N1 are approximately the same, and they will have to equal 10 to the negative third in order for this to equal 1 on the left-hand side of the equation. And this will end up being our initial guesses that we will use in part 2 of the exam as 10 to the negative third 0.0001, or 0.001, sorry. So yeah, that's how we pretty much work out the scaling and the order of magnitude for this problem, and we will use all this information later in part 2 to solve out the actual values of what the fluxes should be and find the graphs of what they will look like. So thank you for coming, and please tune in part 2.